For today's lesson, we will be discussing about the areas under the normal curve. So this is related with our discussion about the normal probability distribution. So just to recall, we discussed last time about the empirical rule, wherein it states how many % of your data must be within 1 standard deviation, 2 standard deviation, and 3 standard deviations away from your mean. So this percentage shows us how many % of your data should be 1 standard deviation away from the mean. So for example, 68.3% of your data falls within the 1 standard deviation away from the mean. So this tells us how many % of our data falls within the specific range of standard deviations. And in order for us to identify this, of course, it's not always 1 standard deviation away from the mean or 2 or 3 standard deviations away from the mean, because our scores can be located somewhere in between those standard deviations. So that's the reason why we use z-scores. So we convert our data into its corresponding z-score for us to identify how far it is from the mean. And we use those z-scores to identify the area within the scope or range. So when we say area under the normal curve, so it is the graphical representation of percentage, proportion, or probability. So the area or the value that we can obtain can be represented using percentage. So percentage is used when reporting about proportion. So we convert it into percentage, and it will tell us how much or what % covers this particular area within the given range. And for the probability, it is used in talking about the chance that an event occurs. So the value that we will get in the area within our z-scores, this can also help us to tell what's the probability that the scores or the data that we will get will fall under this range. Now, to solve for the areas under the normal curve, we use what we call as the Z-table. So this is the Z-table. So this is what we use whenever we want to identify the areas under the normal curve. Now, there are different kinds of Z-tables. So there's a Z-table wherein it's all positive only. And here, what we have is a Z-table with negative Z-scores as well. So remember, this Z-table that I'm showing you here, this shows us, or this represents the area to the left of the Z-score. Left of the Z-score. So for example, let me draw here a normal curve. Something like that. So let's say I want to identify the area given the z-score of 1.68. So given the z-score, which is 1.68, so I just have to locate where is 1.68 from our normal curve. So let's say it's here, 1.68. Now, if you will be using this table, this z-table that I'm showing you, this will give you the area to the left of the z-score. So that means this area, this one, this is what we will get from our z-table. So how are we going to use our z-table? So we have here 1.68. So here in the first column, you will see the z, which represents the z-score. And then all you have to do is to find here where is the whole number in the first decimal place. So that is 1.6. So you just have to locate where is 1.6. So here's 1.6. So let's highlight that one. And since what we want is 1.68, so you have to look at, again, first row. So we have here the second decimal place, 0.00012345 up to 9. But since what we want is 1.68, that means the second decimal place of that will be 0.08. So this one right here. Okay. Now, once you identify where is the whole number in the first decimal place as well as the second decimal place, you now have to identify their intersection. So you just have to look at this one. So here, and also horizontally for 1.6, going to 0.08. So there. So they will meet at that value, this one right here, 0.95352. So that means that is now the area to the left of our z-score, which is 1.68. Okay, 95,352. So let's write here 95,352. So this one, the value that we obtained from our z-table, that is now the area that represents the left side of our z-score, which is 1.68. So this is 0.95352. Remember, area, the total area under the normal curve is 1. So 0.95352 of that falls within this range, which is from 1.68 below. Now, you can also convert this into percentage. So we just have to multiply to 100. So that will give us 95.352%. And this states that our scores below or within this area, 1.68 below, is 95.35% of our data. Okay, so we can use the percentage and also this one for our area. Now, let's try to find the area of scores less than the z-score, which is equal to 1.35. So first thing that you have to do is to draw or to illustrate the normal curve with the given z-score. So this will help us to visualize. Let me just fix that one. This will help us to visualize what part or what region of the normal curve are we trying to identify. So this is the mean, and then all you have to do is just to locate where is 1.35. It doesn't need to be that accurate as long as you know if it's above the mean or below the mean. So here is 1.35, and then let's just write here the boundary. Now, what we want is the scores, area of the scores less than the z-score, which is 1.35. So if it's less than the z-score, that means we are looking at this area right here, or this region, or the area to the left of our z-scores. Because again, what we want is to identify the area of the scores less than the z-score, which is 1.35. Since what we want is the area to the left of our z-scores, so to get the area, all you have to do is to just look at our z-table. Because again, the z-table that we have gives us the area to the left of the given z-score. So let's just go back to the z-table. So again, what we want is to identify the area less than the z-score, which is 1.35. So let's just go over and find 1.35. So here we have 1.3. So this is 1.3, and again we have to go to the column with 0.05, because again what we need is 1.35. So this one right here, and then just look at the intersection of the two. So this one going down up to 1.3, and then this one there. So they will meet at this point, which is 0.91149, and that means that will now be the area of our scores less than the z-score 1.35. So let's write here the area now is 0.91149. So that is now the area. Now, if you want to convert this into percentage, you can just multiply this to 100. So you have 91.149%, or this can be equal to 91.15%. So this means 91.15% of your data scores below the z-score, which is 1.35. Now, you can also use this area for describing the probability of the given boundary. So that means the probability that we will get the scores less than 1.35 is 0.91149. So that also gives us the probability that we will be obtaining the values less than the given z-score. Next, let's find the area of the scores less than the z-score of 0.40. So like what we did a while ago, let's draw again the normal curve. So let's just draw a normal curve just for us to visualize what is happening and what side are we going to identify or look for the area. So this is 0.40. So let's write the boundaries less than. Since this is less than, again, we're going to identify the area to the left of our z-score 0.40. So like what we did a while ago, all you have to do is just to look for the value in the z-table for 0.40, and that will give us now the area of our z-score. Okay, so going back to our table, let's now look for 0.40. So this is 0.4. And then since I want 0.40, so I will be looking at 0.00, the column 0.00. And this one now will be the value. So that is 0.66. So that is 0.65542. So that will be the area below or less than the z-score of 0.40. So let's write here 0.65542. And again, if you're going to convert it into percentage, so that is 65.54%. So rounded off already. And that means from your set of data, 65.54% of that falls below the z-score of 0.40. Next, how about if it's more than? So find the area of scores more than the z-score, which is 2.25. So let's draw the curve and illustrate. So 0, 2.25. So here we have this one. Since this one now is more than, we want to identify the area of the scores more than the given z-score. That means we are looking at the right side of our z-score. So that is what we want to identify. But again, take note, in our z-table, if you look at the values there, it will only give you the area to the left of the z-score, which is this area. This one right here. But again, what we need is the area more than or greater than our z-score, which is 2.25. So what you can do is, to get the area, you can get the area below 2.25 using the z-table, and then you subtract it from 1. Because again, the total area of our normal curve is equal to 1. So that is one thing that you can do. So 1 minus, then get the z-score or the area of the z-score below 2.25. So again, just look at your table. So 2.25, that is 0.98778. And then all you have to do is to subtract. So what we will get is 0.01222. So this is now the area of the scores more than the z-score, which is 2.25. Okay, so that is one thing that you can do. Or if you want, you can look at the negative 2.25. Okay, negative 2.25. Now, what's the relation of negative 2.25 with 2.25? Remember, our normal probability distribution is symmetric within its mean. So it means that negative 2.25 is the same as with 2.25 or the area. Okay, because again, it is symmetric. The only difference is that the other one is to the right and then the other one is to the left. So what you can do is, you can just convert your given z-score into its negative pair. So that is negative 2.25, and then look at the z-score or the z-table. So let's try. So if you will look at the z-score, negative 2.25. Let's try. Negative 2. So this one is negative 2.2 and then 0.5. 0.05. So 0, 1, 2, 3, 4, 5. So this one. Okay, so this is the value. See, we just obtained the same area, which is 0.01222. So any of the two techniques you can use. You can just convert the given into a negative, its negative pair, or what you can do is you can get the area to the left of the positive z-score and then subtract it from 1. So that is what you will do if you're looking for the area of the scores more than the given z-score. So you have two choices. Next, find the area of the scores between z is equal to negative 0.41 and z equals 1.23. So this time we're given two z-scores and we have to identify the area between the two. So again, it's better if you will illustrate. So you can illustrate the curve and then let's write the z-scores. So this is 0. We have negative 0.41, so it's on the left of the mean, negative 0.41. And then we have 1.23. So let's say it's here, 1.23, this one. Now what we want is to get this area in between these two. So this one right here. And again, remember, what we have is the area to the left of our z-score. So what you can do here is, we can take a look at the area of negative 0.41 to the left. So if we will get that, so it will be this one. If we will also get the area of 1.23 to the left of the given z-score, so we will obtain this part right here. But what we need is only this one, because this represents the area between the two. So what we can do is, you can get the area of the two z-scores and then subtract. So if we will subtract the area of negative 0.41 to the area of 1.23, so we will get the remaining, which is this one right here. Okay, so what we will do is, we will subtract. So let's now get the z-scores, or the values for the z-scores to the left of the given values here. So for 1.23, the area of that is 0.89065 minus, then you get the area to the left of negative 0.41. So again, you use the ZTable. That is 0.34090. And then all you have to do is to subtract. So the area now is 0.54975. So this is now the area of the, or area between the two z-scores. If you're going to convert it into percentage, that will be 54.98. So you can just round it off to 2 decimal place. So that means 54.98% of your data is between these two z-scores, negative 0.41 and 1.23. Assuming that your data follows a normal probability distribution. And for our next example, find the area of the scores more than x equals 35, given that the mean is 32 and the standard deviation is 1.2. So here, as you can see, the given is a raw data, which is 35. So we have the mean and the standard deviation. That means we have to convert this first into its corresponding z-score before we can look at the z-table. So let's convert it first. So we have 35. So the x minus the mean, which is 32, all over the standard deviation, which is 1.2. So again, we convert it first into its corresponding z-score, and this is 2.5. Now, let's draw the curve just to visualize. So this is 0, and then we have 2.5. Now what we need is to find the area of the scores more than the given score, which is x equals 35. And its corresponding z-score now is 2.5. So that means, since it's more than, what we want is the area to the right of our z-score, which is this one. So like what we did in the previous example, so we can get the area to the left of 2.5 and then subtract it to 1. So the area to the left of 2.5 is 0.99379. And then you subtract it again to 1. So you will get the area of the z-score, which is 0.00621. So So there. So this is now the area of the scores more than our z-score, which is 2.5. So if you're going to convert it into percentage, so this is 0.62%. So that means 0.62% scored more than 35. So let's say what we have here are scores in an exam. So 0.62% scored higher than 35. So that is how we can interpret this area right here. And for our last example, a group of grade 11 students took a test in mathematics and the final grades have a mean of 70 and a standard deviation of 10. If we can approximate the distribution of these grades by a normal distribution, what percent of the total number of students scored higher than 80? So what we have here is some of the raw scores or raw data, which is what we know is that the mean is 70 and then the standard deviation of the scores is 10. Now we want to identify what percent or how many percent of the students, so the total number of students scored higher than 80. So what we will do here is we will be using the areas under the normal curve, and first thing that we have to do is to convert the given score into its corresponding z-score. So z is equal to, and then we have the score, which is 80, minus the mean, which is 70, and then divide it with the standard deviation, which is 10. So computing for this, we will get 1 as our z-score. Now that we already have the 1, which is our z-score, we can now draw the curve. And then this is 0, this is 1. So what we want to identify is to determine the number or the percent of the total number of students who scored higher than 80. So that means higher than the z-score. So we will be looking at the area to the right of the z-score. So looking at our table, you can look there for 1. That is 0.84134. And then since it's to the right of our z-score, so we have to subtract it to 1. So therefore, 1 minus the area to the left of 1. So we have 0.15866. Okay, so this is now the area. Since what we want is the percentage, so you have to convert it into percentage. Just multiply it to 100. So we have now 15.87%. So 15.87% now is that the percentage of the students who scored higher than 80. Okay, so since this represents this area right here. So that's it for today. I hope you learned something about the areas under the normal curve and how to use the z-scores as well as the z-table in identifying the area, and also how to use it in identifying the percentage, also the probability. And see you next time.